today's lecture, I will discuss a simple composite system, a composite system made up of two subsystems, and you already know the subsystems. I am going to consider a two-dimensional isotropic oscillator, one oscillator along the x axis and the other oscillator along the y axis. Since we have already attempted the problem of the simple harmonic oscillator, it should be possible for us to now consider two such oscillators not interacting with each other, but we are interested in looking at the system as a whole. So, this is the composite system that I am going to consider. It is a composite system of two oscillators. As such, therefore, the Hamiltonian for the first oscillator, which I will represent by H1, is simply half m omega squared x squared plus px squared by 2m, where m is the mass of the oscillator, x is the coordinate, and p sub x is the linear momentum corresponding to the coordinate x. Then there is the other oscillator, which too has the same mass, the same omega, but now it is along the y direction, and therefore I have y and p sub y. So, these are the two independent Hamiltonians, and I have a situation with x, p sub x, commutator is IH cross identity, and that is the same as the commutator of y with p sub y. Since these are independent oscillators, x with p sub y commutator is 0, similarly y with p sub x commutator is 0. That is how I take care of the fact that these are absolutely independent of each other. I could write this in terms of the raising and lowering operators. You will recall that we defined x as a plus a dagger by root 2, except that there was a root of h cross by m omega multiplying that, taking care of the right dimensions, and p sub x is simply root of m omega h cross a minus a dagger by root 2 I. I would do the same thing for the oscillator along the y axis, and I would write y is equal to root of h cross by m omega b minus b plus b dagger by root 2, and p sub y as root of m omega h cross b minus b dagger by root 2 I. In other words, the ladder operators, that is the raising and lowering operators for the oscillator given by this Hamiltonian H1 are a and a dagger. The corresponding ladder operators for the oscillator with Hamiltonian H2, those operators are b and b dagger. So, I would have a dagger equals identity, b dagger equals identity. Every other commutator vanishes. A b dagger is 0, b a dagger is 0, b with a dagger commutator is 0, and so on. So, these are the two independent oscillators. What is the composite system? The composite system has a Hamiltonian which is going to be the sum of H1 and H2. I could write H1 in terms of a and a dagger as a dagger a plus half h cross omega, Similarly, H2 is B dagger B plus half H cross omega. The number operator corresponding to the first oscillator is A dagger A, and the number operator corresponding to the second one is B dagger B. Therefore, if the states corresponding to the first oscillator are represented by this ket n sub A, by A I mean the first oscillator, by B I mean the second oscillator. So, the states which are the energy eigenstates of the first oscillator are represented by the label n sub capital A. So, my composite system is composed of system A and system B, system A being the first oscillator and system B being the second oscillator. Represent the states this way, where Na can take values 0, 1, 2, 3 and so on, and Mb can take values 0, 1, 2, 3 and so on. I reiterate that A and B are simply used as subscripts to show that these are the labels corresponding to one of the oscillators and these are the labels corresponding to the second of the oscillators. And since the energy eigenstate labels take value 0, 1, 2, 3, I have these values for Na and Mb. So, given this, it is clear that A dagger A acting on the state n sub A simply pulls out this number, and we have this eigenvalue equation. Similarly, B dagger B acts on the state M sub B to give me this. The raising and lowering operators, you will recall, act in the following manner. The lowering operator simply pulls out root n sub A and lowers the state label by 1, and I represent it in this manner. Similarly, B pulls out the label Mb under the square root, and I have a lowered state Mb minus 1. The corresponding raising operators are A and A dagger and B dagger, so that I have the following equations, and B dagger acting on Mb gives me root of Mb plus 1 with a higher energy state whose label is Mb plus 1. So, this is what I have by way of equations. I now find out what are the various operators in this problem which commute with each other. Since the commutator of A with B dagger vanishes and they are independent oscillators, it is clear that A dagger A with B dagger B is 0. I have the total Hamiltonian H, which is A dagger A plus B dagger B plus 1 H cross omega, because there was a half H cross omega from the first oscillator contributing here and another half H cross omega from the second oscillator. So, this is the total Hamiltonian for the system. It is evident that the commutator of A dagger A with H is 0 and the commutator of B dagger B with H is 0. So, I should be in a position to simultaneously diagonalize the Hamiltonian H corresponding to the composite system H1 and H2. Suppose I forget the 0 point energy 1 H cross omega for the moment and consider the Hamiltonian to be just A dagger A plus B dagger B. I can always add 1 H cross omega later, and here I have set H cross equals omega equals 1 for convenience. We can always put that back, adjusting dimensions appropriately. So, I will now consider this Hamiltonian A dagger A plus B dagger B and find out the eigenvalues, the energy eigenvalues and the corresponding eigenstates corresponding to this Hamiltonian, and of course, A dagger A and B dagger B, which I already know. It is clear that when A dagger A acts on the combined state of the system, it is merely going to act on the label Na, leaving the other ket corresponding to the second oscillator alone. So, now we have reached a state where we need to define the state space of the full Hamiltonian. So, we postulate the following: the state or the state space of the full Hamiltonian is made up of states which are tensor products of the states of the subsystems. In other words, the net state of the composite system is given by the tensor product of Na, ket Na with ket Mb. This could be treated as a postulate. It is clearly inspired by the fact that even in a single system, there is a superposition principle, and if you have basis states psi 1 and psi 2, A psi 1 plus B psi 2 is also a state of the system. Extending this and inspired by this, you could treat this as the postulate which says that the combined space has states which are tensor products of the subsystem's eigenstates. We have to clearly understand how exactly these operators act on these states. I could use a shorthand notation for this. I could call this Na Mb. Dropping this sign, I essentially mean by this notation this object. I could make it even simpler, and I could write this. By this notation, I would mean this. I would be using all these notations interchangeably as I go along, but any of this would represent the state of the full system. Now, we have the following situation. When A dagger A acts on the state Na Mb, it is clear that it only acts on the states corresponding to system A, leaving Mb as such. Therefore, it is like saying that A dagger A acts on the ket Na, and the identity operator acts on the state Mb. So, this gives me Na Mb. In my notation, this would simply be, where this is a number labeling the state, and this is the net state of the system that is identical to Na and the state written this way. Similarly, when B dagger B acts on the state of the system, it works in the following manner. It is like the identity operator acting on the states corresponding to system A, tensor producted with this, and therefore, B dagger B pulls out an Mb from here, that is a number, leaving me with the state Na Mb. Now let us look at operators like A dagger B. So I extend this. First of all, B acts on the state Na Mb, leaving Na alone and pulling out root Mb, which is a number from here. Of course, A dagger has to operate on the net state, and the net state is now Na Mb minus 1. The action of B on the ket Mb was to pull out the value root Mb and lower the state by 1, leaving Na as such, the ket Na as such, and then A dagger acts on the state Na. When A dagger acts on the state Na, pulls out a value root of Na plus 1, raises the state label by 1, leaving the system B untouched. So this is the net effect of the operation of A dagger B on the state Na Mb. Similarly, we can work out the action of various operators on these states. Let us look at the algebra of these operators. Now that we have described how exactly the operators act on the states, let us find out the commutator of the non-Hermitian operator A dagger B with its Hermitian with its counterpart B dagger A, its Hermitian conjugate B dagger A. Now this acts on the state Na Mb of the system, and what does it do? When I expand the commutator, I simply have two terms, A dagger B, B dagger A acting on the state, minus B dagger A dagger B acting on that state. I use the rules that have been defined earlier. So this is A dagger B, B dagger A acts on the state Na Mb. First of all, A simply pulls out root Na, reducing the state label by 1. B dagger acts on Mb, increasing it by 1. So that is the effect of B dagger A on Na Mb. It is clear that B dagger is the raising operator on this state, and therefore the label went up, and A is the lowering operator on this state, and therefore the label went down. That is the first term. Minus B dagger A, which acts on the net state A dagger B ket Na ket Mb. So once more, when B acts on Mb, it pulls out root Mb, lowering the state to Mb minus 1, leaving Na untouched. And when A dagger acts on Na, it takes it to root Na plus 1, and the state label is raised by 1. So this is how the commutator expands. So let me proceed and complete the simplification. I have in the first term the numbers root Na, root Mb plus 1, which I can pull out, and then A dagger B acts on these states. So B acting on Mb plus 1 and A dagger acting on Na minus 1. That is what I have here. Here A, so this would simply give me an Mb, and A dagger acting on Na minus 1 would take it to Na. So the net state would be ket Na ket Mb. The coefficients are obvious. B acting on Mb plus 1 pulls out a root of Mb plus 1, and A dagger acting on Na minus 1 pulls out a root Na, leaving behind ket Na, ket Mb. That is from the first term. Similarly, the second term gives me the following coefficients: A on ket Na plus 1 gives me root Na plus 1 ket Na, and B dagger acting on ket Mb minus 1 pulls out root Mb, increasing the label by 1. So, this is what I have for the commutator of A dagger B with B dagger A acting on the state Na Mb. Let me simplify this. I have A dagger B with B dagger A acting on the state Na Mb of the composite system to be simply Na Mb plus 1 minus Mb Na plus 1 multiplying the state Na Mb. So, this is what I have. This is the commutator that I have. Now, consider the effect of the operator A dagger A minus B dagger B acting on the state Na Mb. Now, this clearly simplifies. Na Mb cancels out and I just have Na minus Mb out here. Consider the action of the operator A dagger A minus B dagger B acting on the state. This is simply Na minus Mb Na Mb. So, indeed it looks like I have proved that A dagger B commutator with B dagger A is twice A dagger A minus B dagger B by 2. This is the relation that I have. I have very deliberately put a 2 out here and divided by 2 so that I may define this as a Hermitian operator, where I have a commutation relation which is similar to what I knew from the SU2 algebra. I had S plus with S minus is 2 Sz. So, now I would like to check if indeed I can mimic the angular momentum situation using these two oscillators, and in fact that is the purpose of my talk today. This composite system was selected by me to see if I can reproduce the angular momentum algebra using two harmonic oscillators. If indeed I can identify this with Sz, I should be able to check out the analog of the commutator of Sz with S plus and Sz with S minus, which is what I will proceed to do now. So, let me consider the commutator A dagger A minus B dagger B by 2 with A dagger B. That is the same as the following. I could do this, for instance, by just applying the ABC rule. In order to make things very clear, I will do it explicitly by attempting to find out its effect on the states. In other words, I would like to repeat the procedure and find out the action of this commutator on the state Na Mb. So, that is half A dagger A minus B dagger B commutator with A dagger B NaMb. So this is the same as finding the commutator of A dagger A with A dagger B acting on NaMb minus half commutator of B dagger B with A dagger B acting on the state NaMb. It is pretty clear here that A dagger commutator with A dagger B is 0. I could use the ABC rule, and then I find that the only non-vanishing contribution comes from the commutator of A with A dagger, and that is 1. Similarly here, the only non-vanishing contribution in the commutation comes through the commutator of B dagger with B, and that is minus 1, and therefore this becomes a straightforward matter. So this is the same as half. I can pull out A dagger on this side, commutator of A with A dagger, B, NaNb, minus half A dagger, commutator of B dagger with B, B, which is the same as half A dagger B from the first term, and this is minus 1, and therefore plus half A dagger B from the second term acting on NaMb, which is the same as A dagger B acting on the state NaMb. In other words, I have shown that A dagger A minus B dagger B by 2 commutator with A dagger B is plus A dagger B. In a similar vein, we can find out the commutator of A dagger A minus B dagger B by 2 with B dagger A and check that this is minus B dagger A. I have therefore got the SU2 algebra. I have a situation where I have identified 3 operators, 2 of them being Hermitian conjugates of each other, and the third being a Hermitian operator, satisfying the following commutation relationship. And this is simply the SU2 algebra. So I identify A dagger B as the raising operator. I could call it J plus, B dagger A as the lowering operator, and you would recall that this is the same as the Hermitian conjugate of J plus, and I can identify A dagger A minus B dagger B by 2 as Jz. I would like to call this J plus, J minus and Jz by way of notation, because I am not looking at a particular spin system or orbital angular momentum. This is the general angular momentum algebra which I have generated, and therefore I refer to these as J plus, J minus and Jz. Before I proceed, I would like to comment about the dimension of the full space. Once we do a tensor product of the individual subsystem states, the dimension increases in a certain fashion. For instance, if system 1, subsystem 1 and subsystem 2 have just 2 basis states, this is subsystem A and that is subsystem B. Suppose they have just 2 basis states. This is an example that I am considering. I refer to them as 0A and 1A and 0B and 1B respectively. The tensor product will give me the following basis states. And the last is 1A tensor producted with 1B. So there are 4 basis states. It's pretty clear that if subsystem A had 3 basis states and subsystem B had 3 basis states, then you would have a total of 9 such states. Now if I just look at qubits, each qubit is like a spin doublet. There are 2 states as in this example, and if I put a collection of n qubits, the composite system of the n qubits has 2 to the n basis states. Now in general, if I want to deal with a large system, I could take a single system with 2 to the n basis states, n being sufficiently large, or I could work with a set of n qubits, each qubit having a 2-dimensional linear vector space, as in this case. In other words, I can have small subsystems, in this case each is a qubit, a doublet. I could combine a large number of them and provide 2 to the n basis states for the composite system, instead of choosing a single system with a very large linear vector space, in the sense that it is a single system with 2 to the n basis states. Now normally, if it is a single system where the basis states are the eigenstates of the Hamiltonian, the 2 to the n basis states are the energy eigenstates, and therefore reaching out to the higher energy states would mean expending that much energy. It means going to higher energy levels of a system. Instead, I could work with 2 to the n qubits, with n qubits, and provide 2 to the n basis states. That could be cheaper for me in terms of an experimental arrangement. That is merely a digression. It is a point worth remembering for our future lectures, when we will talk about interacting systems. But right now, getting back to this point, I can now define the analogues of Jx and Jy. You will recall that J plus was Jx plus Ijy and J minus was Jx minus Ijy. Therefore, Jx is J plus J minus by 2, and Jy was J plus minus J minus by 2i, and therefore I can write Jx as A dagger B plus B dagger A by 2, and Jy as A dagger B minus B dagger A by 2i. I emphasize that Jy is Hermitian because J minus dagger was J plus, but there is an overall negative sign, and that is taken care of by the fact that I, its complex conjugate is minus I, and therefore I have these Hermitian operators. It will automatically follow that Jx Jy is Ijz, and this is a cyclic relation. This can be explicitly checked out, but it will work out simply because I have obtained the SU2 algebra already in terms of J plus, J minus and Jz. Now let me look at the action of A dagger B, that is J plus, on the combined state of the system. So A dagger B acts on the state Na Mb. As I said before, B acts on Mb to pull out root Mb, lowering this to Mb minus 1, leaving the state ket Na alone, and A dagger acts on the state ket Na, pulling out a root of Na plus 1, raising the label to Na plus 1. But I know that when J plus acts on the state J comma M of the composite system, I should get root of J minus M times J plus M plus 1 J comma M plus 1. So I'd like to now identify little j. I know little m. Little m is clearly the eigenvalue corresponding to the state j comma m, corresponding to the operator jz. You will recall that I have said h cross equals 1. And since jz is A dagger A minus B dagger B by 2, this implies that m is simply Na minus Nb by 2. And therefore, I have identified m. It is clear that the values of m can be either integer or half integer, because when n sub a is 0 and n sub b is 0, m is 0. But when this is 1 and that is 0, for instance, I get m equals half. When Na is 0 and Mb is 1, that is an m. When Na is 0 and Mb is 1, it is clear that m is minus half, and so on. So this quantity m can take integer and half integer values, and these could be positive or negative. That is as I would expect from angular momentum algebra. In order to identify and make the connection between root Mb root Na plus 1 with root of j minus m j plus m plus 1, let me consider the total number operator n, which is A dagger A plus B dagger B. Its eigenvalues are clearly the sum of the eigenvalues of A dagger A and B dagger B. So let me call the eigenvalue corresponding to the operator n as little n, that is Na plus Mb. So let us make a neat column, tabular column, and what do we see? When Na is 0 and Mb is 0, n is 0. Na and Mb can only be integers, and therefore n can only be an integer. So let me start, and since these are 0 or positive, n can only be 0 or positive. So let me put n equals 1. This could come from Na equals 1, Mb equals 0, or Na equals 0, Mb equals 1. In other words, the eigenvalue n equals 1 could come from the state 0a 1b or 1a 0b. So as far as the composite system is concerned, n equals 1 is a doubly degenerate state. There are two eigenstates, distinctly different eigenstates, which correspond to the eigenvalue n equals 1. Suppose n equals 2, Na could be 2 and Mb could be 0, Na could be 0, Mb could be 2, or Na could be 1 and Mb could be 1. So what are these states? This would be a 2a 0b. The second one is a 0a 2b, The third one is a 1A, 1B. So, there are 3 states corresponding to n equals 2. It is obvious that the degeneracy for a given n is n plus 1. There is an n plus 1 fold degeneracy corresponding to a given n, coming from various combinations of NA and NB. So, for a given n, there is an n plus 1 fold degeneracy. Consider the object n by 2. So, let us make a column n by 2, NA, NB. When n is 0, n by 2 is 0, NA is 0, NB is 0. We might as well make a column NA minus MB by 2. So, when n is 0, NA is 0, MB is 0, and NA minus MB by 2 is 0, but this object is simply M. When n by 2 is half, I find that NA could be 1 and MB could be 0, giving me M equals half, or NA could be 0 and MB could be 1, giving me the value minus half. So, you see, it looks like n by 2 is to be identified with j, and we will check it out with n by 2 equals 1. In other words, when n is 2, n by 2 is 1, and what do I have? I have m values 1, 0 and minus 1. I would like to call n by 2 as j. J takes positive values 0, half, 1 and so on, and for a given value of j, m takes values minus j to plus j in steps of 1. And therefore, I have now identified j. In terms of operators, H was A dagger A plus B dagger B, and what we are looking at is the operator H by 2, which is A dagger A plus B dagger B by 2. So, now returning to our problem, we had a situation where A dagger B acted on NA MB to give root MB root NA plus 1, changing the state to ket NA plus 1, ket MB minus 1. So, let us look at what this is going to be. Consider root of j minus m into j plus m plus 1 and expand this in terms of NA and NB. This is NA plus MB by 2 minus NA minus MB by 2. That is the first term. The second term is NA plus MB by 2 plus NA minus MB by 2 plus 1, and all this within the square root, under the square root. So, this is just going to be root of MB from here, and this just gives me an NA plus 1, which is what I have here. And therefore, it is clear that when A dagger B acts on this, it acts precisely in the manner in which the angular momentum raising operator acts. I have identified root MB times root NA plus 1, which is what comes out when A dagger B acts on the state as the coefficient. I have identified that with root of j minus m into j plus 1 m plus 1, where j itself is NA plus MB by 2 and m is NA minus MB by 2. Therefore, the angular momentum algebra is complete. We have shown that starting with two oscillators which do not interact with each other, we can produce the angular momentum algebra by suitable combinations of A dagger, B and B dagger. We have identified Jx, Jy and Jz. We have identified J plus and J minus, and also checked out that little j, small j, can only take values 0, half, 1 and so on. And for a given j, there is a 2j plus 1 degeneracy in M. We have also checked that in terms of energy eigenvalues, given n, there is an n plus 1 fold degeneracy in the case of the two-dimensional oscillator. Let me now extend this to a three-dimensional isotropic oscillator and at least check out the extent of degeneracy. So, in the case of the three-dimensional oscillator, isotropic oscillator, I have these three independent oscillators. The notation would now be evident. H is A dagger A plus B dagger B plus C dagger C. Of course, there would have been a 3 by 2 H cross omega, half coming from each of these oscillators, but we will choose to forget that for the moment. Our aim is merely to find out the degree of degeneracy of every eigenvalue, and therefore, the analog n in this case is given by Na plus Mb plus Lc, where A dagger A acts on the state Na to give me eigenvalue Na, B dagger B acts on the state Mb to give me this eigenvalue equation, and I have a corresponding equation for the system C, the subsystem C. So, let us look at what would happen here. Each of these could take values 0, 1, 2, 3 and so on. N also would take values 0, 1, 2, 3, and therefore, we make a table in the case of the three-dimensional oscillator. I have N, Na, Mb, Lc. When n is 0, they are all 0. When n is 1, I have the following three possibilities. All these correspond to n is 1. When n is 2, I have these 6 possibilities, and so on. It is pretty clear what is the extent of degeneracy. For a given value of n, so when n is 0, there is exactly one state. The label is 0, 0, 0, if you wish. When n is 1, there are 3 states. These states would carry labels 1, 0, 0 or 0, 1, 0 or 0, 0, 1. By this I mean this state would mean Na equals 0, Nb equals 0, Nc, Lc equals 0 and so on. So, I have an n plus 1 times n plus 2 by 2 fold degeneracy for a given n. So, both in the case of the two-dimensional oscillator and the three-dimensional isotropic oscillator, there are states which are degenerate in contrast to a simple harmonic oscillator. This is the simplest composite system that we will consider for the moment. Subsequently, in my lectures, I will talk about interacting systems which are composite systems.